Introduction to Venn diagrams. It is a topic that, depending on where you are in math, you're going to eventually run into it. Now, sometimes students may not, depending on the type of math they get. So Venn diagrams in general are pretty useful, actually, if you're a visual person. It allows you to break things down when you get into ordering things and grouping things, and you talk about the different types of sets. So I want to introduce Venn diagrams to you in this video. So what you see here on the screen is the typical way that we would represent kind of by two circles, which will represent kind of two subsets of the main entire set S that you see here. And we would input how many items we have in each. Notice that they intersect there, because if you put the two circles and you kind of bring them closer enough together, you'll see an intersection point where an item belongs to both of the circles. So let's explain this by a very simple example. So let's say that I have that my set S, and notice so these double dots, okay, this just means is defined as. So it's defined as these natural numbers, which only go up to 20. So it's 1, 2, 3, 4, and so on, up to 20. So that's my S. So S is my set. It's a collection of these items from 1 to 20. Then I have created two subsets, okay? So subsets doesn't mean that it actually includes all the items from 1 to 20. So I created the first subset, I called it SA, and I'm defining it as kind of 2, 4, 6, and then 8. So basically all the even numbers. And then I created another subset, okay, of the original set S, which is 2, 3, 5. Okay, now in this case, it's basically all the prime numbers. And now, if I wanted to kind of show how many, now each of those numbers or each of the elements in each set, so I use the word element, so we say an element or an item is basically, one particular thing in that set. So for us, 1 is an element, okay, of the set S, okay? 2 is an element of the set S. Now notice 2 also belongs to SA, and it also belongs to SB. Okay, so it has in those sets as well. Okay, so we have these elements that we can use, and now these Venn diagrams. Okay, so Venn, so it was basically a logician. I think it was somewhere in the maybe 18th century or something like that, that he lived, and maybe early on in the 19th century, and he passed away. So he used this representation when you wanted to be able to visualize these sets. In particular, when you have an overlap between sets. So whenever you have an overlap, it's nice to have this. So overlap means that there is items, or there are items that belong to both sets. Okay. So within here, if I would draw this out, I can actually state how many of these items are in each of the set. I can also put the items in those sets so that we can visually see them. All right. So I'm going to do two things here. So I'm going to borrow this, and I'm going to draw, because you'll see that this is what the Venn diagrams are used for. So I'm going to duplicate this and put it here at the bottom. Okay, just right here. So first, what I'm going to do is I'm going to put these items, okay, within here. So if you notice, okay, so the number 1 is not in any set, okay, so within here. So if this was right here, so if this is the SA, and this would have been the SB, then the number 1 would belong somewhere outside of that set, okay, so that would be that number 1. Number 2 actually belongs in both SA and SB. So, I can put the number 2 in here, right? Number 3 is a prime number, and it only belongs in SB. So, I can put it right there. Number 4 is only an even number, so I can put it right here. 5, okay, is a prime number, right? 6 would go in here. 7 is prime number. 8, okay. 9 actually does not belong to SA or SB, so it would be kind of outside. of this particular range. It's not a prime number at all because we can divide it by 3. The number 10, so that's even. Number 11, so that is actually prime. 12, okay, so that would be here. 13 is also prime. 14, so 14 would be here. 15 does not belong to either the sets. It's not prime and it's certainly not even. 16, okay, so 16 we can put in here. 17, I can put into there. 18, and then I guess 19 would be the last one in here, and then 20 would be here. So you notice that within this, those are the actual elements, and then you can visually see where they belong. So we do this kind of a rectangular box in here to designate all the items in that set. Now that set doesn't have to be finite, okay? Now finite meaning that it has a finite number of elements. It could be infinite. S could have been, for example, all the natural numbers, and so that could have been an infinite set. But the idea behind the square is just to show that that is the set that I am dealing with. And then we put the circles in these Venn diagrams to represent the other sets. Okay, so now in this case we have two subsets. SA and SB are the subsets of S. So you will sometimes find, okay, that you can designate this like that. So SA is a subset of S. So that means that all the items in SA belong to S. Okay, so that's what a subset will be. And then the same thing, SB is also a subset of S, of the entire thing. All right, so we have elements, we have these subsets. Now, we also have kind of the intersection there. So within here, you notice that, so right here, so as I would kind of draw this out like this, that's the intersection between the sets. And we can write that out. So the intersection would have been SA intersected, so we use this symbol, with SB. So that's the intersection, okay? Symbol between, and that is just what is in both of the sets. So there's only one item. 2 is the only one that belongs to both, and that's what's nicely captured in this Venn diagram, that you can actually see that happening. Okay. Now, the other component that you should also know as you're studying these Venn diagrams, because you're going to run into it, you can also be asked, okay, so how about the union? Like, what if we took all the sets in SA and then all the sets in SB? So what if we took all of these sets, these two sets, and all the items within? So then you can write, and that we write as SA union, so we do it the opposite way. This would be SB. So that's the union between the two sets. Okay, we don't really add plus because plus means it's the addition, okay, between. Union means that you're taking one set and then you're adding it to the other. And then we can list all the items. So in this case would have been 2, 3, 4, 5, 6, 7, okay, 8. 9 is not there, it would have been 10, then 11, 12, and so on. So we can create the actual union, and we can write it out as a set formation in the brace brackets as well. So these things are kind of useful. And now what you will find is, in studying these Venn diagrams, oftentimes we're asked questions as, how many items are there, right? In terms of maybe the intersection between the two, or how many total items are there? So what's the union, okay, of all the different sets? What's the total number of items? Now we can count them, right? We can just say, oh, okay, someone wants to know how many items there are. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say the total 9. So 10, 11, 12, 13, 14, 15, 16, 17. Right, so there's total 17 items. Or we could have said, okay, well, there's 3 items outside. In total, I had 20. So 20 minus the 3 would have given us the full out answer that we would have. All right. So that's something that we can use. Now, in order to ask, how many, total items there are, or how many total elements there are, we like to do something like this. We like to say n, which is the number of, okay, And then it's almost like a function where we say n, and then we're inputting the set S, and we're asking, okay, so how many total items were there in the set S? And we know that there are 20. We can also ask, okay, so how many total items were there in the intersection between the two sets, like this? Well, there's only one item, so this would be equal to 1. And so that n that you see there, and then in brackets we put in whatever sets we want to be able to count, we do that. And so what I want to do here is, so for instance, if you were just interested, okay, here in the numbers, so not in the actual elements, so you can actually say, okay, well, how many did we have? Well, we had 3 items, right, that were outside of those two sets, those even and prime. We had 1 item in here, so that was the 1 item that was the intersection, okay, in between, that was my 2. And then we had, so within the even numbers, we had 1, 2, 3, 4, 5, 6, 7, 8, 9. So that were 9 items inside here. So this was my SA. Okay, and now I am actually counting. So, sometimes you might see this, and SA. Okay, so how many total numbers there are in here? How many total numbers are in here? All right, and then, that intersection, we would have written N, SA intersected with SB to be able to count this up. All right, now I can check what that is. I can certainly count them up as well. So the prime numbers, so there's 1, 2, 3, 4, 5, 6, 7. So there's 7 in here. So now in total, if we would do this, we would have N SB. So that is equal to the 7 plus the 1, right, which was intersected. Total in SA is equal to the 9 plus the 1. So that would have been 10, okay, within here. So that's what we have. And we can do that counting. All right. So this is pretty useful, and this is called the Venn diagram, where you do have some kind of an overlap. If there is no overlap at all, there's no items that are shared in between, and we typically will say that those two sets are mutually exclusive. You might hear that word at some point. Okay. So as soon as there is overlap, we can use this Venn diagram. And Venn diagrams are not just used, with 2 particular subsets. It can be 3, it can be 4. The only thing is that visually, especially in 2 dimensions, really if you go up to only 3 subsets, you can draw those 3 circles to be able to visually kind of see what's happening. But if you go to 4 and beyond, the Venn diagrams are not very good because we can't visualize them, okay? Because there's just too many sets, and the overlaps that happen in between the sets are not nicely captured. So I would say, a maximum kind of 3 subsets within here, okay, that you will be able to do. And I'll do an example like that as well so that you can see it. All right, so how we can use these Venn diagrams. All right, so let's see it. Okay, let's see now an application of this, because you certainly typically are not going to be dealing with just kind of numbers. You're going to be dealing with some situations with these Venn diagrams. So here's our first simpler example, and we're going to try to break it down, answer the questions, and then, create these Venn diagrams for it. So it says a school has 21 students on the swim team and 48 students on the track and field squad. So there are 7 athletes on both teams. Okay, it says now create a Venn diagram for this example. So I'm going to, borrow this just so that I don't have to kind of replicate the whole thing. So here's my Venn diagram. I'm going to copy it. And in this case, we have 2 subsets within here. So we have so I'm going to remove these right here. Okay. And so I'm going to list them out. So we have a swim team, which is one subset. And then we have a track and field team or squad, which is the second subset. All right. So let's, so this would be, let's say this is the swim team. This is the track team. So I'll put it like that. Now, in my overall, so there's certainly the total number of students that maybe either do track, swim, or both. Okay, so let's try to see what happens. So it tells us that we have 21 students on the swim team. So that's the total number on the swim team. Okay, so I'm going to write that down. I'm going to write it at the bottom here. So the swim team, okay, has 21 students. Then it tells us that we have 48 students on the track and field squad. So this is for track. And we would have, so this is 48 right there. And now we have in both, so swim and in track. Okay, so we have that. And now for this, there are 7 on both. So if I wanted to create a Venn diagram, I have to be careful. I can't really put, 21 or 48 like this, because of the fact that 21 means that it's the total number, right, that we have. So what we typically will do in these Venn diagrams, you would start actually from the intersection, from the overlap in between. So we know that there are 7 students that overlap. That means they do both swim and track. And now, because you know that there are 21, so within here, so 21 are in total, minus the 7, which is the overlap. So that leaves us 14 on the swim team that only do the swimming, plus the 7, which also do track, and 14 plus the 7 now gives you the 21. While on the track team, you had 48, so that means 48 in total, minus the 7 that overlap. This would have been 41 that only do track. So you can see that now, if you wanted to know, okay, and then answer the rest, for instance, part B says, what is the total number of students participating in just one sport? So to answer that, well, only in one sport, well, it's either this plus this. So that would have given us, so 14 plus the 41. So that would have been 51 and 55. So there are 55 athletes or students that only do one sport. So that would answer that question. And we can see that from the Venn diagram. For part C, what is the total number of students participating in at least one sport? Okay, so in at least one sport, that means that we actually have to take the union. So now we have to take the union in between here. So all of this, all right. Okay, so we would have that, and we can count them. So that's 14 plus the 7 plus the 41 would have been 62. All right, so that would have been 62 items, okay, that do at least, so at least one. And it would have been 14 plus the 7 plus 41, which I guess is 62. All right. Now, to be able to, without seeing the Venn diagram, and then counting them up individually, you can actually, if you do know the total number, okay, that's swim, and you know the total number that do track, and you know how many do both, then obviously you can say 21, because 21 were the total number of swimmers, 48, which is the total number of track. But notice now we counted 2 times the ones in the middle, so we would have to subtract so that we don't overcount them. So it would have been 21 plus your 48, okay? And notice 21 plus 48, so that's going to give us 69. And then minus the 7 is going to give us the 62, which is exactly the same. So you can go about finding the union in between the two sets in kind of 2 different ways. All right? Now, in general, if someone does give you a set and then gives you the total for the other set and then the total for the intersection, then the total number in between, so if you wanted to know, so the total number, okay, if you wanted to know, so let's say one set, so set A in union with set B is equal to simply the total number of SA plus the total number in SB And because we have that intersection, we want to subtract whatever there was intersected between the two sets. All right, so this you can use in general as a formula, but if you're only dealing with two subsets, then visually Venn diagrams are super nice to be able to do that. So that's how we can do a Venn diagram, okay, with two examples. All right. Now I am going to do another example, except now it's going to be with three subsets, okay, and then how we can find out and do those answers and draw it. But I'll put up a link up above there, okay, in case you would want to be able to see it. For now, okay, this is it as the introduction to these Venn diagrams, okay? You can watch the other video if you want to see another example of these Venn diagrams in place, and then I'll do even one more with 4 subsets. And for that one is a little bit more challenging. All right, thanks for watching. We'll see you in a future video. Bye, everybody.